All right, so today is the last calculation about in QED itself. After that, we'll start talking about some quantum, well, the setup for the quantum corrections. So today we'll consider one step further in complication of calculations in QED, and we'll consider a process that contains two diagrams. I mean, in principle, there was nothing stopping us last calculation. In fact, one of the exercises was to consider Baba scattering that had two Feynman diagrams. But, well, we will consider this now, and also one more ingredient, which is sum over photon polarizations. We did sum over spins for fermions, but it's sometimes useful also to consider sums of photon polarizations, as we will see. And so the process we'll calculate is unpolarized, so sum over spins, Compton scattering. Compton scattering means the scattering of a photon of an electron, right? So the interaction, well, in this case at 3 levels, so equivalent to a classical calculation, interaction between the photon and the free electron. So one way to describe that would be to say, well, there's a free electron moving around, some momentum p, and, well, ended up with a momentum p prime, and then there is a photon coming in, momentum k, and it scatters, and it's therefore re-emitted from the electron. So classically it would just bounce off, but quantum mechanically it's absorbed and then re-emitted. So this would be the natural diagram that we could think. But then, of course, this is quantum mechanics. So that's relativistic and quantum. So the process of where the photon is first absorbed and then re-emitted is on the same footing as the process where it's first emitted and then absorbed. So the order of the two processes is opposite. So let's say first K prime and then K. Okay, so there's nothing, quantum mechanics, there's nothing preventing this other process. On the other hand, now, so this is sort of the view, having in mind a semi-classical viewpoint where the electron is the main player here and the photon just bounces off of him. But we can rewrite these Feynman diagrams also. I mean, in some sense, just straighten up in a different way the lines in the diagram. And we can say that the first diagram is this, while the second diagram let's say is this. Okay, so P, K, P prime, K prime, K prime. So it's really the same diagram. We just are emphasizing that this is what we usually mean by the photon being absorbed and re-emitted, whereas this one has a slightly different interpretation where things occur roughly speaking, at the same time, the two processes. All right. So now let's use the Feynman rules to write the sum of these two diagrams. So we go in the opposite direction of the Fermion line. So u bar of p prime, then let's call this mu and this nu. So then plus e gamma mu. And then this is a photon being emitted, so must add the photon polarization for emission. Photon polarization being epsilon mu of momentum k prime, and star because it's being emitted. Then minus p slash plus, so let's write here first. So if this momentum is p, this is k, here we have p plus k, but then this is p, this is p, this is k prime, then this would be p minus k prime. So, so the momentum on the first diagram is p plus k for the intermediate particle, and the second one is p plus k prime. So here, p plus k plus im, p plus k squared plus m squared. Then plus e gamma mu for the second vertex, and epsilon mu of k, and finally u of p. That's the first diagram. Now the second diagram, u bar of p prime, the same thing, plus e gamma mu of the vertex. But now, let's see, how do I use this? Yeah. So in the second diagram, I want to use the same convention as in here, where the external momentum is not only k prime but also mu. So here I'll put mu. That means here I'll put mu. Epsilon nu of k. Here also epsilon nu of k. So so in that case, the vertex in here will be this gamma nu, epsilon nu of k, and then minus p slash minus k prime slash plus IAM over p minus k prime squared plus m squared, and then epsilon mu, plus e gamma mu, epsilon mu star of k prime, and finally again u of p. Okay? All right, so let's take some common factor outside. This. So minus e squared. And also the epsilons, because that's why we consider them to be the same. Epsilon mu star k k prime epsilon mu of k. And then also we have u bar of p prime on one side and u of p on the other. So then here we have gamma mu p slash plus k slash plus im gamma mu over p plus k slash squared plus m squared, and in the second term plus gamma mu p slash minus k prime slash plus im gamma mu over p minus k prime squared plus m squared, and then u of p. All right. So so now let's try to simplify this a little bit before we calculate in detail. So first we have this numerator p plus k squared plus m squared. So that's p squared plus k squared plus 2pk plus m squared. So this is a photon, so it has zero mass, and this is an electron, so it has a mass m. P squared plus m squared then is zero, and also k squared is zero. This is 2pk. And then also the same thing here. Cancel this and this. This is minus 2k prime. And then further, we see that we have a combination here, p plus k plus im, that is something like what it would appear in the Dirac equation, but we have a gamma mu in the middle. But anyway, after that we act on u. So let's see what that gives. So the k, of course, we cannot do anything because here we have u of p, but p slash plus im gamma mu u of p is equal to, now of course we have to commute p slash plus gamma mu. Im of course commutes trivially. So gamma mu is minus gamma mu plus 2g mu, right? And then this is multiplied by p mu, right? So this is equal to gamma mu. I put it on the other side, and here I get minus p slash plus im, then u of p, plus 2g mu, 2g mu times gamma mu, so that is plus 2 gamma mu. So this is plus 2 p mu, right? No, wait, what am I saying? No, I'm yeah, sorry. Yeah, I should have said like this, right? That's 2 p mu. Sorry. And now we remember that this acting on this acting on u of p is just the Dirac equation. So therefore the only non-zero term is the remaining 2p nil u of p. Now similarly, well, no, sorry. Yeah, that's the only thing that happens because we have this combination both in the first term and in the second term. Well, the only difference is what we call this gamma. One of them we call mu, the other we call mu. All right, so given this, I can write Im as minus the common factors, minus e squared epsilon mu star of k prime epsilon mu of k u bar of p prime. So we get one term that remains, gamma mu k slash gamma mu. And then we have this term 2, gamma mu p mu plus 2 gamma mu p mu. And the first denominator was 2pk. Then the second term is minus gamma nu k prime slash gamma mu minus gamma nu k prime slash gamma mu. Let me write it here. Minus k gamma nu k prime slash gamma mu. And then plus 2 gamma nu p mu over 2, this second denominator is, sorry, minus 2 p k prime, and then u of p. All right? All right, so this is Im. But we are interested in a cross section, so we need also Im complex conjugate, or minus Im complex conjugate. And in order to compute that, you see we have u bar p prime, u of p on the other side, and in the middle we have some gammas, right? So we have to generalize what we saw previously, namely we saw that this was equal to minus u tilde bar gamma mu u, and so the way we've calculated this is by using first complex conjugation as dagger. So on a number they are the same thing, and therefore writing this in opposite direction. So u tilde, yeah, and this is u dagger I gamma 0, and then this is u tilde dagger gamma mu dagger I gamma 0 dagger, that is minus I gamma 0 dagger. And yeah, and this one was equal to gamma 0, right? You remember gamma wait. gamma 0 was equal to my convention. I'm getting confused, I think. Sorry?
The gamma I is emission and gamma 0 is
Yeah.
then you get minus 1 to the u and then cancels when you commute.
Yeah. That's right. I see now. Yeah, so this is minus gamma 0. So then this was plus I u tilde dagger gamma mu dagger. Well, yeah, I gamma 0. But then this is equal to minus. When I go to the other side, I get a minus sign, so u tilde dagger I gamma 0 gamma mu and u. And then this is u bar. Okay? So we use this relation. And then
stands for, sorry.
different ones. Different ones.
Oh, so there's the,
Yeah.
there's the indices would be different. That's what I mean.
No, different spinors, right? So u of p versus u of k or something, some other spinor.
Yeah, that's what
Can it be as well?
And then, so similarly, then we can do this with several gammas. And so again, we find that this is u tilde dagger gamma mu n dagger until gamma mu 1 dagger I gamma 0 minus I, well, yeah, I gamma 0 dagger, which is I gamma 0, as we saw, and u. And now this hopping on the other side will get a minus 1 to the n, because we go past n of them. U tilde dagger I gamma 0, which is u tilde bar, gamma mu n until gamma mu 1 u. Alright? So,
should it be an extra minus sign because you're commuting u tilde and u? It won't change the calculation, but just the expression.
well,
Because the calculation, there's always pairs, so it won't change. But here,
no, they're not always pairs, right? That's the point. That I have u bar and u, just that.
yeah, in this case, it doesn't have pairs.
Yeah, so, no, I think it's like this.
It's
I think I'm pretty sure it's like this because I got it.
But it's an extra minus overall, so it won't change too.
Because when
Yeah, but
take
you will
the
get,
dagger-
it will mean that the d sigma d omega is negative, which is wrong. Right?
The step is complaining because when you take the dagger of the whole thing, then you invert the order. Don't you get a minus when you tilt the passes to you into this?
Well, anyway, we'll see that we'll get a positive one, so we did the calculation correctly. So let me write it here. So u bar gamma mu 1 gamma mu n u tilde minus 1 to the n u bar tilde gamma mu n gamma mu 1 u. So right, so then in minus I star, complex conjugate of this. So, the complex conjugate of this gives so the same factor in here because this is all real, and then in here we'll have u bar, and in the middle we have either 3 gammas or 1 gamma. But either way, this is an odd number, so I will get a minus 1 to the end gives a minus. So the minus turns into a plus in here. Means plus e squared epsilon mu star of k prime epsilon yeah, I should use a different dummy variable because mu is already there.
What about complex conjugation?
Sorry?
Shouldn't you complex conjugate?
Yeah.
Right. So I should complex yeah, so k prime should be this and yeah. And I should use a different dummy variable, so now I have to be careful. So mu was in the same order as in here. Now I have rho sigma, but when I complex conjugate, I get the different order. So now I have u bar of p, and then gamma sigma k slash gamma rho plus 2 gamma rho p sigma over 2p k prime plus minus gamma, well, so initially I have gamma sigma gamma rho, now I have gamma rho gamma sigma, gamma rho k slash gamma sigma plus 2 gamma sigma p rho, 2pk here and here minus 2pk prime. And here u of p prime. Okay. All right, so we have written the basic element, but now we have to sum over spins. And we remember that the sums over u's will give us p slash and so on. So that is fine, but we now have also to sum over the polarizations of the photons. So over epsilon mu, which are the analogs of u's and v's. So we have to figure out how to do this first. Photon polarization sums. So we would have things like, like for instance, epsilon mu star of k prime with epsilon rho of k prime, right? So in general then, we have things like, so let's call them epsilon mu star of k and epsilon mu of k. We'll have things like this. And the rule that we want to prove is that the sum of polarizations is equivalent to just replacing this with G mu nu. So let's see that. So, however, what that means is that, so specifically what that means is that I have to have in the amplitude I have to have an epsilon mu star of k, m mu of k, right? Like we have in here. And then sum of polarizations of m star would be sum of polarizations of epsilon mu star of k, epsilon mu of k, n mu of k, n star mu of k, right? And so what we want to see is to show that this would be equal to g mu m mu k n mu of k, n star mu of k. All right. Yeah, I think I want to write here in the middle. I don't need this anymore. So, why is that? Well, we will use the word identities. And in this case, they will imply that k mu m mu of k will be equal to 0. And the reason is we've seen this for 1pi functions. So we've seen specifically this thing, and then generically k mu1 for gamma mu1 mu n of k equal to 0. All of these were Ward-Takahashi identities that we've derived. And then, so these were all 1pi. But then in the S matrix, as we know, we have what? Well, we have a connected and amputated endpoint function, right? So when we amputate it, and then contracted, of course, with polarization tensors, right? Like we see here, we have the polarization tensors, and then everything else that's contracted with it, it's a 1pi function. So, well, in the case of this diagram, so these things were external, were external lines, which are polarization tensors, and the remaining thing was a 1pi object. Well, sorry, it was well, this is not 1pi, but corrections would be 1pi. So really what we have in here is the gamma itself, which is the propagator. So yeah, we have the propagator plus 1pi. Okay. And the propagator itself satisfies the same formula. The propagator satisfies that k mu delta. Well, yeah. How should I say this? It's not exactly propagator. It's well, yeah, k mu in this case, k mu times the vertex is still equal to 0. So by the same logic by which the vertex with endpoint, it's also transverse. So the point is that then for all of the components possible in the S matrix, we still have that k mu m mu of k is equal to 0. And another way of seeing that, that's perhaps more intuitive, is to say that m mu of k can be understood as, well, the momentum space of Fourier transformed. But then what happens is that you have a transition between an initial and a final state. But this m mu of k is really the current by which we mean this psi bar gamma mu psi. The thing that appears in the action that's multiplied by a mu. Right? So in the action we have a mu times this object. So then this integral j mu a mu is thought of as the current coupling inside the Lagrangian in the action. All right, and given that this is basically a momentum space current in between some states, the current itself satisfies d mu j mu equal to 0, right? This specific object satisfies it. And then in momentum space that becomes k mu j mu equal to 0, right? And then putting it in between some external states f and I still maintains it, so maintains its property. So that means this k mu m mu has to be equal to 0. So this is a more formal way of saying the same thing, namely that k mu m mu equal to 0 is a manifestation of gauge invariance. So gauge invariance, word identities are, Ward-Takahashi identities rather, are a manifestation of gauge invariance at the quantum level on the Feynman diagrams, and k mu m mu is then understood as the current conservation at the quantum level. Current conservation is really, through this coupling, is the same as gauge invariance of the coupling of the gauge field to the matter, right? All right. So all of this is the general theory, but in the specific case that we have in here, you could, if you want, you could just check this, right? I mean, you have m, so by removing this one, say, you get m mu, and then you can just see, if you put a k mu in here, you'll get k slash, right? And here also here you'll get k prime slash k slash. Oh no, sorry, this is k prime, yeah, this is k prime, so multiplying with k prime mu, I get k prime slash k slash, and gamma nu And then on the other side I get let's see, so why does this well, plus 2, let's see, plus 2 k prime slash p nu over 2 pk you get from the first term, and the second term you would get minus gamma nu k prime slash k prime slash, right? So that's the same as k prime squared, which is equal to 0. Plus 2 gamma nu p k prime, but then this is over minus 2 p k prime. So all of this second term then reduces to minus gamma nu. Okay, and in here pk, in here how do I show that this is 0 to pk gamma nu. Yeah, don't see this. It's not completely obvious. I think you probably have to use also the Dirac equation. Dirac equation for p or p prime. No, for p, because I have p. No, but that doesn't work, because there is no p slash. Well, k prime slash k slash gamma nu plus 2 k prime slash p nu. And then from the denominator I have minus 2 pk gamma nu. Somehow this has to give 0. Yeah, that sounds strange. Why is this true? Well, I have certainly that p plus k is p prime plus k prime. Yeah, that doesn't help. I have just pk k prime. Well, okay, I don't see it. I know it's supposed to be true. I just don't see it. All right. This is bizarre. I don't see why this is true, and I cannot. Well, or maybe it is only when I multiply with epsilon nu of k, because that's also there. Yeah, maybe that's the point. But I cannot see it now. Epsilon nu, gamma nu. And this has to be 0 for some reason. I mean, I know it is true, but I just cannot see it. Why is this? Because everything else, I mean, u bar of p prime, u of p, I don't think makes any difference. There's no p slash anywhere. Ah, well. Okay, sorry about this. I'll try to think about what this is, why this is 0, but I think maybe maybe we have to go back to the original form. No, oh, I see. Oh, it is true. I still don't see why I can not prove it in here, but yeah, if I go to the original form, well, let me write it here quickly. So I'll just show it for. So in fact, it's moreover, it's true in the original form. It's true Feynman diagram by Feynman diagram. So I write the first element in IM was U bar of P prime, E gamma mu, epsilon mu star K prime. So there was minus as well, and P star plus I plus K, P slash plus K slash plus IM, or P plus K squared plus M squared, E gamma mu, epsilon mu of K, U of P. So this was just the first Feynman diagram. And as I said, oh no. Oh, with K prime I cannot do. I think the point is, yeah, maybe it's easier with just epsilon mu of K. Yeah. If I remove this and I replace with K mu, then I get here K slash, and then K slash is K squared, which is 0.
The direct equation.
And then, yeah, so I need to go to move K slash past P slash, and I get minus P slash plus IM on U, which is 0. But when I do this, I'm still left with pk. So it's actually not 0. Huh. Okay, I don't know. I thought I had it, but apparently I don't. There's some proof in here that I don't seem to have found. Anyway, for some reason this is supposed to be true, which I cannot see why, but that's it. Assuming this is true, so as we said, we have a general argument why K mu and mu of K is supposed to be 0. That's just gauge invariance on the Feynman diagrams. And then choosing specific orientation for K mu. So let's say K mu is in the Z direction. Remember, K mu is a photon, so the energy is equal to momentum. So choosing this, for instance. Then the two physical polarizations are transverse, so in the directions 1 and 2. This would be 0, 1, 0, 0. and 2 would be 0, 0, 1, 0. So then k mu, m mu of k equal to 0. With this one, with this form of k, this becomes k times m 0, well, minus m0 plus m3. Equal to 0. So m0 equal to m3. And then sum of polarizations, epsilon mu star of k, epsilon mu of k, m mu of k, m star mu of k, becomes so epsilon 1, let's say, so this sum of polarization means sum of 1 and 2. And in the case of 1, we have just the one component, so m1 star in the case of 1. And then in the case of 2, we have just the 2 components, so m2 star, right? And you see this is absolute value m squared, this is absolute value m squared with component 1 and 2. But then components 0 and 3 are equal. So I can write this for free as minus m0 squared plus m3 squared. And then this m1 squared plus m2 squared. But this is just d mu m mu star mu. Okay, so given that k mu m mu of k is equal to 0, the sum of polarization just reduces to replacing this object with g mu. Okay. So we've proved our recipe.
But I don't think I don't know if it's important, but you're considering epsilon both of k, not k and k prime.
Yeah.
It doesn't change anything.
No, it's supposed to be the same k, right?
But here they're different.
No, the assumption was, I said, if m is an epsilon of k times some m that also depends on k, right? I mean, it doesn't have to be, you know, it has to have k somewhere, and it does have it somewhere. It has it here, for instance, k, and k prime has it here, right? So
that's when you calculate m squared.
right.
Modulus of m squared.
Okay, so right. Okay, so let's erase here. And say now that we can sum of a spin, we can calculate 1/4 sum of spins m squared as so we have im times minus im star, then we have the sum of polarizations. Sum of polarizations in U and U bar, which gives P slash plus M, P slash minus M. And then we have the sum of polarizations in epsilon of k prime and epsilon of k. And as we saw, the sum of polarizations in epsilons amounts to replacing with g mu. So let's write what we get. We have minus e squared times plus e squared, so minus e fourth. Then from here I have minus epsilon mu star of k prime, epsilon mu of k, and from there we have epsilon rho of k prime, epsilon sigma star of k. Right, so this then is replaced by g mu rho, and this is replaced by g mu sigma. Okay, so g mu rho, g mu sigma. And then in here we'll get the usual trace. And let's see how we get that. We get so let's see first. We get this u bar of p prime. And from this you get u of p prime. So u of p prime times u bar of p prime is minus I p prime slash plus m. Then this factor, gamma mu k slash gamma mu plus 2 gamma mu p mu over 2 pk minus gamma mu k prime slash gamma mu plus 2 gamma mu p mu over 2 pk prime. Then u of p and u bar of p. This gives minus I p slash plus m. And now this other factor, gamma sigma k slash gamma rho plus 2 gamma rho p sigma over 2 pk minus gamma rho k slash this is plus minus upstairs. Minus downstairs, yeah. So gamma rho k k prime gamma sigma plus 2 gamma I forget gamma rho gamma sigma p rho minus 2 pk prime, and that's it.
Yes.
Yeah.
Why are we still dividing by 4 the result? Because we don't have 2 fermions in the beginning.
But we have 2 polarizations for photons.
And
It's the same.
Yeah. And then you have you were forgetting this 1/4 the ray inside of the equation.
Oh, yeah. All right. So now I can erase this and copy it. Already. And so minus E4 over 4. And so I contract mu with rho. Oh, here, second term is k rho, k sigma. Okay, and then the remaining mu is sigma. Well, maybe use the other color. And I want to write this as I want to separate the terms according to the denominators. So I'll write 1 over 2pk squared. That means this term times this term, plus 2 over 2pk prime, by which I mean this term times this term, plus 3 over 2pk prime 2pk. I mean, the order just says which term it is this times this, plus 4 over 2pk prime squared. Okay. And then we note what? So first of all, we note that 2 is equal to 3. So if I contract this with this, or this with this, I get the same thing. Let's see. So because you see, in the first one I have contraction of the first 2 gammas and contraction of the last 2 gammas. And here also have contraction of the first 2 gammas and the last 2 gammas. It doesn't matter that the dummy variables are different, they're dummy variables. So it's the same term. So 2 equal to 3. And then 4 is a little bit different. So 4, you see, there's a sign difference, right? So there's a sign difference in the first term with respect to this, and also here I have k, here I have k prime. So this is replacing k with minus k prime. All right? So that means that I really only need to calculate 1 and 2. The other ones are obtained for free. All right. All right, so now gamma matrix identities, fun stuff. So 1 is equal to trace of. So minus I p slash prime plus n. Then gamma mu k slash gamma mu. Plus 2 gamma mu p mu, then minus I p slash plus n, then sigma is equal to nu, gamma nu, k slash gamma mu, plus 2 gamma mu p mu. All right. Okay, so how many traces there are in here? Well, we have 2 times 2 times 2 times 2. We have 2 to the 4, that's 16 terms. Right? But in here we have, so each one, this is 1 gamma, this is 0 gamma, this is 3 gamma, this is 1 gamma. So because of this and of this, there are half terms which have even number of gammas and half terms that have odd number of gammas. So the odd number of gammas gives the traces 0. Right? So that means that from this we have 8 non-zero terms. Okay, so let's write them independently. And well, it's useful to consider the number to consider them in the order of how many gammas you have. So let's consider the largest number first. So we keep the largest number in each bracket. So we have minus I from here times minus I from here. So minus trace p prime slash gamma mu k slash gamma nu p slash gamma mu k slash gamma mu. Okay. And 3, 6, 8, yeah. And let's see, what do we want? So we have this thing first. This thing was calculated before, so gamma gamma nu, gamma nu, gamma nu. This was equal to minus 2 gamma mu. We've calculated that before. So minus with minus, that's wait, I think I have a sign mistake in here. Anyway, let me continue because I seem to find already a sign mistake, and that's very bad because in the notes I did this calculation several times. So okay, so minus I times minus I is minus. Then I have this minus 2, which means plus 2 all in all. Trace p slash prime gamma mu k slash, and here I have p slash k slash gamma mu. And here I can commute these things. I can write this as minus k slash p slash. Remember, slash means gamma, so when I change the order I get a minus sign and then plus 2 times the contraction, so 2pk. But then k slash times k slash, and always is k squared, which is 0. So this term goes away. And so I get 2 times 2pk trace p prime slash gamma mu but this is equal to just 4, and I did something wrong. 3, 6, 8, what? I forgot somewhere something. This has 8 gammas, it's supposed to be non-zero, but I forgot the gamma somewhere. Let's see, 3 gave 1, so Now I have 3, 6, okay. Now after this I have 4, so p prime slash gamma mu. Yeah, k slash. K slash gamma mu, okay. And again, this is equal to, well, yeah, I can use the same relation I used here. So this is equal to minus 2 gamma gamma nu. So this is minus 2 k slash. All right, so minus 2 times 2 times 2 is minus 8 pk trace p prime slash k slash. But trace gamma mu is 4 g mu, and so in this case I get 4 p prime k, so minus 32 pk p prime k. Okay, I got the right result. So I don't know, probably had an even number of mistakes in my notes. All right. Then let's consider, let's see, how did I, yeah, well, it doesn't matter. If I call them differently, the traces, it doesn't matter. Important is to get all the terms right. Okay, so let's see. Let's consider next this with this, and now instead of this, with this, right? That's also an even number of gammas. So again, minus I squared, that's minus, trace p prime slash gamma mu k slash gamma nu, p slash, and then 2 gamma mu and p mu. Oh, okay. And since it's p mu, I can put it here already. So p slash, right? And but p slash is p squared, which is minus m squared. So this is equal to plus 2m squared trace p prime slash gamma mu k slash gamma mu. And this thing, as we saw, is minus 2k slash. So this is equal to minus 4 m squared trace p prime slash k slash, and this is equal to 4 p prime k, as we did before. So this is minus 16 m squared p prime k. Okay. Then I3. Let me consider now. Let's see what else. Yeah, okay. Let's consider with this the opposite. So these terms again with the same ones from these two brackets. So minus I squared, it's still minus trace trace p prime slash gamma, well, 2 gamma mu p nu, then p slash gamma mu k slash gamma mu, and p nu with gamma nu is p slash. And again, this is p slash, which is p squared minus m squared. This is minus, plus 2m squared, trace p prime slash gamma mu k slash gamma mu. But again, gamma mu k slash gamma mu is minus 2k slash. So this is equal to minus 4m squared trace p prime slash k slash. This again is 4p prime k. So again minus 16m squared p prime k. Okay. What else? Let me consider for completeness also just to finish with this combination with p prime slash and p slash. Let me consider also this term, where I take the second terms in the two brackets. So let's call this I4. Again, minus I squared, which is minus, trace p prime slash 2 gamma mu p nu, then p slash 2 gamma mu p nu. And p nu is p squared, that's minus m squared. And then I have 2 and 2, so 4 minus minus plus, so plus 4m squared trace p prime slash gamma mu p slash gamma mu. This is minus 2p slash as everywhere before. So this is equal to minus 8m squared trace p prime slash p slash, and this is 4p p prime. So this is minus 32 m squared p p prime. All right. What else? Yeah, I think seem to need everything on the board. Well, I can squeeze things here, but let me find a few places which are clean. So all right. So now we have terms with m, with m from the beginning. Right. So we've finished the terms where I have both of these things, right? Both p and p prime. Now, if I have only one m in here and one p slash, that doesn't work out because the remaining number of gammas is even, right? So together with this one would be odd numbers. That's 0. So the only possibility is keeping both m's. So let's say I5. So all of these terms that come next start with m squared. And let's start with these two. So m squared trace of gamma mu k slash gamma mu gamma nu k slash gamma mu. Well, this is equal to 4, and this, putting on the other side by trace cyclicity, is also equal to 4. Right? So this is 16 m squared trace k slash, but this is k squared, so that's 0. Okay? Then I6. The other possibility would be this with this. So I have a factor of 2 there, 2m squared trace gamma mu k slash gamma mu times gamma mu p nu. And p nu, I can put it here as p slash. And then again, by cyclicity, I put gamma mu in the last position. And gamma mu is 4. So this is 8 m squared trace k slash p slash. This is 4kp. All in all, this is 32 m squared kp. All right, and yeah, this is gonna get ugly, but let's consider here. So I7 would be this with this now. And so this is m squared trace. Well, there's a factor of 2, so then then gamma mu p nu and gamma nu k slash gamma mu. This is p slash. This again is 4. So this is 8 m squared trace p slash k slash. This is 4 pk. So 32 m squared pk. Same as I7. And finally, I8 is this with this. So that's m squared trace. And here I have, well, as you can see, p nu, p squared. Then gamma mu, p squared, which is equal to minus m squared. And this is 4 times 1, but the trace of 1 is 4, so this is 16. So all in all, this is minus so wait, there was m squared, but then I had also a factor of 4 coming from these 2's. So 4 times 16 is 64, minus 64 and 4. Yeah. Okay. All right, so then let's write this 1, which is sum from 1 to 8, I, which is equal to. First one is minus 32 pk p prime k. So minus 32 pk p prime k plus I2 and I3 are identical, so minus 32 m squared p prime k. Minus 32 m squared p prime k. And I4 is minus 32 m squared p prime. 32 m squared pp prime. I5 is 0. I6 is equal to I7 and is 32 m squared pk. So plus 64 m squared pk. And I8 is minus 64 m4. All right? Good. So now, all right, so let me write this factor 1 in here, in the corner. 1 was equal to 32, or minus 32, common factor, and then pk p prime k, pk k, plus p prime k plus pp prime, m squared p prime k plus m squared p prime, plus 2 m squared pk, 2 m squared pk minus 2 m4. Write it here. And this 2 and 3, 2 equal 3, is left as an exercise, because you also have to get proficient in this boring thing. And the result is minus 16 minus 2k k prime p prime plus 2k p prime p plus m squared p prime k minus 2k prime p prime 1, 2, 3, 4 1, 2, 3, 4 minus m squared p prime k prime plus m squared p p prime no, what am I? Minus 2k k prime p prime plus 2k p prime p plus m squared p prime k minus 2k prime p prime minus m squared p prime k prime plus m squared p prime. Oh, that's fine. Minus m squared k prime plus 2m squared pk minus 2m squared pk prime minus m4. Okay. So this is an exercise.
Professor, just for us not to carry the arrow forward, the last two terms in one have wrong signs because of you put the minus sign in evidence, right? The last two terms you copy with the wrong sign. Just the first
Hey,
term,
have a
not the
number
second.
of signs.
Oh, in here.
Yeah. Last two.
Let me see. Last two. I copied the wrong sign.
Yeah, you copy from there,
Yeah.
from this part to the top.
Minus 32. Minus 32. Yeah. Okay. Thank you.
Just do it.
All right. So now let's write this in Mandelstam variables, because all of these are Lorentz invariants, but all Lorentz invariants can be written in terms of the Mandelstam variables. So let's see. S is minus p plus k squared. That's minus p squared plus k squared plus 2pk. And k squared is 0. That's photon, and minus m squared is equal to minus p squared is equal to m squared. So this is m squared plus 2pk. And on the other hand, by momentum conservation, this is also equal to p prime plus k prime. So minus p prime squared. Minus, sorry. Minus k squared, 0. This is plus m squared minus 2p prime k prime. So this is also m squared minus 2p prime k prime. Then t is minus p minus p prime squared. This is momentum transfer. So this is equal to minus p squared minus p prime squared. This is 2m squared plus 2p prime. 2m squared plus 2p prime. And by momentum conservation, this is also equal to minus k prime squared. Momentum transfer for the photon as well. But then that's minus k squared minus k prime squared, both of these being 0, plus 2kk prime. So this is equal to 2kk prime as well. And u is minus k prime minus p squared on one hand. So that's minus k prime squared minus p squared plus 2k prime p. This is 0. This is m squared. So this is equal to m squared plus 2k prime p. And by momentum conservation, this is also equal to minus k minus p prime squared, which is minus k squared minus p prime squared plus 2k p prime. And that's 0, that's m squared. So this is equal to m squared plus 2k p prime as well. All right. And also you could check this specifically in these forms, but you also have to remember our relation that s plus t plus u is the sum of all m's. And in this case, two lines are photons, so have 0 mass, and two lines are electrons, so have mass m. So this is 2m squared. All right. So now let's erase in here in the middle and try to write down our result. So 1 is equal to minus 32 times pk p prime k. Well, this is from here, right? So pk, that means pk is equal to m squared minus s over 2. And p prime k is p prime k u. P prime k is u minus m squared over 2. Plus m squared p prime k is again p prime k is again u minus m squared over 2. then plus m squared pt prime. Pp prime is t minus 2m squared over 2. Then minus 2m squared. Pk is m squared minus s over 2. And then plus 2m4. Let me check. M squared. Yeah. All right, so let's rewrite this a little bit. So minus 2. Then here we have minus SU, the leading term in S and U. Minus SU over 4, sorry. Then plus m squared times u over 4 from this term plus s over 4. U over 4 plus s over 4. Then from this term it's another u over 2 with u over 4. That gives 3 u over 4. And then plus t over 2. And then minus s over, no sorry, this is 2m squared times this. So this is plus plus s plus wait. Seem to have done something wrong, no? Should be 5, no? I have s over 4 from here and s from here. Okay, I seem to have something wrong in the notes. I hope that doesn't propagate. But then let's see the m squareds, m4. Sorry. So here I have minus 1/4. Here I have minus a half. Here I have minus a half. No, minus 1. This is 2. Minus 1. Here I have minus 1. So yeah, I can already cancel the 2 with the minus 1 and minus 1. And so all in all I have minus 3/4. So minus 32. Okay, so I just have yeah, I have a intermediate error in my notes. So yeah, so that's the correct result. But now we want to, so we'll write this as 1 over 4, 3u plus 5s plus 2t. And I just want to write this to eliminate the t, to write just in terms of u and s. So then I write this as u plus 3s plus 2u plus s plus t. But u plus s plus t is 2m squared. So this would be 4m squared over 4. That's m squared minus 3/4 here would remain plus 1/4. So minus su over 4 plus m squared u plus 3s over 4, then plus m4 over 4. Okay. And then this is I want to put a 2 inside, so minus 16, and this is minus a half s minus m squared u minus m squared plus m squared s minus m squared plus 2m4. Let's see if that's correct. So the leading term is minus su over 2. That's right, there's a factor of 2 that's been multiplied. Then plus sm squared over 2 plus um squared over 2. So I take care of this and one more s from here. And I'm left with 2s over 4, so s over 2. But 1, 2 is outside, so that's the s in here. And then here I have minus m4 plus 2m4, that's m4. But there was one factor of 2, so that's m squared over 2. Oh, but there's also one more here. So minus m4 over 2. So all in all I have m4 over 2, which is the same as this m4 over 4 once I take care of the 2. Alright, so the number 1 factor is written like this. And then similarly, again left as an exercise, we find that 2 equal to 3 equal to minus 16 m squared over 2 s minus m squared plus m squared over 2 u minus m squared plus 2m4. And then 4, as we said, is one where I exchange k with minus k prime.
In 2 and 3 you don't have this overall minus in the rows.
Oh, sorry, yeah.
Just not to carry.
Yeah, thank you. So, so I replace k with minus k prime, but then I look what happens in this case. You see, when I exchange k with minus k prime, then t is invariant. I can look at this formula or at this formula. Anyway, t is invariant. But here is not. P plus k turns to p minus k prime, which is u. So this amounts to s interchanged with u. Okay? So I just take this formula and I switch s with u. The first term is invariant, and the only term that changes is the second one. So then I'll write write 4 is equal to minus 16 minus a half s minus m squared u minus m squared plus m squared u minus m squared plus 2m4. Okay. So then finally, I can write 1/4 sum of the spins m squared is equal to so I have in 1 I have a minus. I can put it in front of that. So minus 16 times minus e4/4, that's and I also erased things that I shouldn't have. I have these denominators here, so I'll rewrite here that s is equal to m squared minus 2pk and is equal to m squared minus 2p prime k prime. T is equal to m squared plus 2pp prime and equal to 2kk prime. And u is equal to m squared plus 2k prime p equal to m squared plus 2k p prime. All right. Yeah, so I can. All right, so I can take this minus 16 as a common factor, and then I write 4e to the 4 times. 1 is divided by 2pk, and 2pk is m squared minus s over 2. Oh, sorry, it's 2pk squared, so m squared minus s over 2 squared. Oh no, there's no 2, yeah, it's 2pk, yeah. It's m squared minus s squared, yeah. Then, minus 1 half s minus m squared u minus m squared plus m squared s minus m squared plus 2m4. This is 1. Then plus 2 and 3 add up, and they also the denominator is also the same. So I just have a factor of 2, and 2pk prime. 2pk is m squared minus s. 2pk prime is m squared minus u. Is u minus m squared. M squared minus s u minus m squared. Then a factor of 2 for the 2 and 3 together. There's a minus sign as well because I've taken out minus 16. And here I have 16. And then m squared over 2 s minus m squared plus m squared over 2u minus m squared plus 2m4. And finally 4 over 2pk prime. 2pk prime is u minus m squared. Squared. And in here, minus 1 over 2 s minus m squared u minus m squared plus m squared u minus m squared plus 2 and 4. Oh, okay. Yeah, I guess I can put plus in here and switch the sign. And the denominator as well. And, all right, that's it. So this is 4e to the 4 times here write also s minus m squared squared. Okay. So, in this term, s minus m squared, 1 cancels with 1 here, and I get minus 1 over 2 u minus minus 1 over 2 u minus m squared s minus m squared. Then the second term is plus m squared s minus m squared. Then plus 2 and 4 over s minus m squared squared. Let me consider this term next. I get the same thing. Yeah. Here I will get the same thing. Just erase this. I get a factor of 1. Oh no, sorry. What am I saying? No, minus a half. This and minus a half s minus m squared over u minus m squared. And then the second term is m squared over u minus m squared. And the last is 2 and 4 u minus m squared squared. And then these terms in the middle. Together I have m squared over u minus m squared, and then m squared over s minus m squared. And the last term is 4m squared over 4 and 4, sorry, over s minus u squared, s minus m squared, u minus m squared. This gives a factor of 2. And minus 1/2 minus 1/2. Yeah, plus 2m squared of m squared plus this. And then these three terms can be also rewritten as 2m4 1 over u minus m squared plus 1 over s minus m squared squared. And that's it. All right. So finally, we've come to the relativistic cross-section. The relativistically invariant cross-section is this sigma dt. And as we saw last time, this is 1 over 64 pi p1 p2 squared minus m1 squared n2 squared times this amplitude squared with 1/4 sum of the spins. And so the only thing to calculate now is this thing. So P1, P2 refers to the initial momenta. So P1 is equal to P, P2 is equal to K. So then I have PK squared. And then M1, M2, this is M squared, but this is 0. So this this second term doesn't exist. And then pk, this was, so I said that s was equal to m squared minus 2pk. Pk was m squared minus s over 2. So this is so this is equal to 1 over 64 pi times s minus m squared over 4. Right? Times 1/4 sums of a spins m squared. And so now substituting, this thing was 4e to the 4. The 4 cancels one more in the denominator. So we get 1 over 4 pi s minus m squared squared e to the 4 times that bracket. So minus 1/2 u minus m squared s minus m squared minus 1/2 s minus m squared u minus m squared plus 2 m squared u minus m squared plus 2m squared f minus m squared plus 2m4 1 over u minus m squared plus 1 over s minus m squared squared. Okay, and then if you want, I can, remembering that e squared over 4 pi is alpha, I can write this as 4 pi alpha squared. So that's the final formula for Coulomb scattering. Well, I will not do this here, but in principle one can obtain also a spin averaged form of the Klein-Nishina formula for d sigma d cos theta, which is easily obtained from this. T is related to cos theta. But then one has to rewrite the Lorentz invariance in the lab frame in terms of these thetas, and moreover the frequencies omega and omega prime. So this would be k0, this would be k prime 0 for the photon, and the result is the following: omega prime over omega plus omega over omega prime minus sine squared theta. So this one looks slightly simpler than this one. And then in here one can find also that the relation between the two is this, just from energy and momentum conservation. So this is a form that is perhaps more useful if you think about observing the frequency of the incoming and outgoing photon, right? Because Coulomb, so this Compton scattering is really, I mean, you're shining a beam of photons, and then you have some approximately 3 electrons, and then you're measuring the scattered photons. So this is something that is of experimental relevance. This is a sort of theoretically interesting formula, but as I said, in the case of the actual experiment, we're measuring distance, omega, omega prime, and theta. All right, so that's everything I wanted to tell you today. Do you have any questions? Well, if not, let's stop here.